You hit record? Oh, you did? All right, I'll start. Dearly Father, we thank you for this day. I thank you again for these students. We thank you for homework being over. I just pray you be with us today. Help us to make good use of this time and to glorify you, Lord, in what we do. You know my prayer, Lord Jesus. Amen. Okay, so today I'm going to give you an introduction to what's known as exterior calculus. You say, well, what is exterior calculus? Well, exterior calculus is basically the calculus of differential forms. So I'm going to talk about differential forms. In R3. So what kind of differential forms are there in R3? Turns out there are just four kinds. You've got zero forms, you've got one forms, you've got two forms, and you have three forms. Those are your possibilities. And in reality, you've been working with these objects all along. Zero forms are just functions. So something like a function f, just a function from R3 to the reals. Plain old garden variety functions. A one form is something like, let's say, alpha equal to a dx plus b dy plus c dz. Well, you've been integrating those for a few weeks, actually, right? b dx plus q dy plus r dz. This is an example of a one form, essentially. What's a two form? Well, this is where it starts to get weird. Beta is equal to something like a dy wedge dz plus b dz wedge dx plus c dx wedge dy. So here this thing is called wedge. So it produces, let's say, the wedge product. I'll tell you more about that in just a second. Three forms. Turns out there's just one three form. Well, one kind of three form. Gamma times g dx wedge dy wedge dz. So here are the a, b, and c on the one form and the two form. These are all functions in general, all right? And the g is a function, f is a function. That's basically it. Now, the wedge product. How do you explain what a wedge product is? Well, I'm just going to be very formal here, and say that the wedge product works as follows. On one forms, you have something like this: dx. Well, let's see. Suppose alpha 1 and alpha 2 both one forms. Then it works like this. Alpha 1 wedge alpha 2 is equal to minus alpha 2 wedge alpha 1. That's kind of the fundamental fact about the wedge product is on one forms it's antisymmetric. It's just like the cross product in that regard. Right? So what does this say about, dx and dx? So like dx wedge dx is equal to what? Minus dx wedge dx, right? Which is what? Yeah, that says 2 times dx wedge dx is just 0. So therefore dx wedge dx is equal to 0, right? So likewise, dy wedge dy is dz wedge dz. Those are both 0. On the flip side, you see why I only had to include just one. Like, why don't I also have to include dz wedge dy in my sort of archetypical 2 form? Why does it suffice to be completely general just to include the dy wedge dz? Well, dz wedge dy is just minus this, right? So I can take the dz wedge dy terms and just lump them together with this one. So there's really only 3 fundamentally independent 2 forms. The dy wedge dz ones, the dz wedge dx ones, the dx wedge dy ones. All right? Let me work an example. Now, furthermore, past this, basically, I would just say, in a nutshell, you proceed normally. Nothing to see here, all right? So, for example, if I had, say, dx plus 2 dy plus 3 dz, and I was to take the wedge product with, say, 4dx plus 5 dy plus 6 dz, just to be boring, what would happen? You distribute, right? So I got like dx wedge 4dx plus 5 dy plus 6 dz plus dy, plus rather 2 dy, right? Wedge 4dx plus 5 dy plus 6 dz. I regret making so many terms non-trivial here. Plus 3 dz, wedge this whole thing, right? So if you don't mind, I'm not going to write out too much more. I'm just going to jump straight to, like, I've got terms with dy wedge dz, right? I've got other terms that have dz wedge dx. I have still other terms that have dx wedge dy. So maybe you guys can tell me, what are the numbers that go in those parentheses? Can you see it? Let's see here. So yz is, so that's 12. And then this is z. So you said minus 15 because it's in the wrong order, right? Okay. And then let's see what's the next one. Zx. Well, this one's in, my color coding is going to become somewhat stupid. I only use red. Let's see here. So x and z will give, but the wrong order, right? So minus 6. And zx plus 12, right? And let's see here. xy. So I get 5. yx minus 8. So just to collect my thoughts then, what I have is minus 3 dy wedge dz plus 6 dz wedge dx minus 3 dx wedge dy. Okay, at this point, it's useful for me to try to introduce some language because, this in and of itself is, fun math we can all do together. Great, but it's much more interesting if I can link it to what we were doing this semester, right? So in particular, alpha, what I've written here, is actually known as the work form, or I use an omega, of the vector ABC. So actually, this differential form, ADX plus BDY plus CDC, is the differential form which corresponds to the vector field ABC. And this next one is the 2 form which corresponds to the vector field. This is the so-called flux form mapping. Here we have ABC. So this is the work form correspondence, work form map. This is the flux form map. think I first found this notation in Darling's book, but it should be in more books anyway. This is not an entirely standard notation, it's just one I use. But anyway, once we've introduced the notation, we can reinterpret the previous example in a very, very natural way. What am I looking at here? This example, what this shows is the work form corresponding to the vector field, constant vector field in this case, 1, 2, 3, wedge product with the work form corresponding to the constant vector field 4, 5, 6 is equal to the flux form corresponding to the vector field -3, 6, and -3. Do you notice anything special about that last vector I wrote? What's the dot product of -3, 6, -3 with 1, 2, 3? -3 plus 12 minus 9, otherwise known as 0. -12 plus 30 minus 18. Wait a second, that vector is perpendicular to both of the inputted vectors. It must be what? The what? No, we're not there yet. It must be the cross product. It's got to be the cross product of these two. That's not entirely, I mean, up to a scale factor, it has to be the cross product. In fact, this is straight up the cross product of those two. So the wedge product naturally encodes the cross product in this way. Or if you want me to write this more symbolically, we have the following identity. Omega of vector A wedged with omega of vector B is equal to the flux form of A cross B. Oh, yes, I'm sorry. Thank you. I wouldn't have been able to sleep tonight if I didn't fix that one. Let's see here. Now, you're like, well, is the wedge product just the cross product then? Well, one of the very important things about the cross product is it gives you an example of what's called a non-trivial Lie algebra. A Lie algebra is a non-associative algebra. And the cross product is one of the first examples because it is in fact not the case that A cross B cross C is unambiguous. In fact, this is very ambiguous. If you see your book, if you have a book that is, you have in engineering or in physics that writes this without parentheses, that's the author's way of telling you they don't know math. Because this doesn't mean anything. I mean, you have to put this. This is not generally equal to A cross B cross C. All right, so to not write parentheses there is, at a minimum, lazy, and at a maximum, ignorant. I don't know. Maybe it's a little bit of both. You need these parentheses. These parentheses are important. On the other hand, guys, it is in fact true that omega A wedge omega B, no vector here, wedge omega C is unambiguous because this is in fact true. So in other words, key property, the wedge product is associative by construction, which is a big difference between it and the cross product. I guess there's a natural question to ask. Okay, so wait a minute. If omega A wedge omega B is the cross product, then what is the triple wedge? So let's figure it out, right? What's, you get omega A, wedge omega B, wedge omega C. We know that this is the flux form of, well, let me work out a different identity before I do that one. How about that? Let's just look at the flux form of, say, ABC wedged with the work form of EFG. All right, so what's that? That gives us an A dy wedge dz plus b dz wedge dx plus c dx wedge dy, that thing, wedge product with e dx plus f dy plus g dz. This is a fun one to take because most of the things are 0. So like if you look at yz, right? If you think about this dy term, you get what? You get dy wedge dz wedge dy. dy wedge dz wedge dy, which is equal to minus dz wedge dy wedge dy. But this is 0. Fun fact, the wedge product of 0 is 0. Sad. Way short. Okay, so in other words, the only thing I actually have to care about is this one. And I can rewrite this as AE plus BF plus CG. And check it out. So like I have dy wedge dz wedge dx, right? But that's the same as dx. Well, that's the same thing as dy wedge minus dx wedge dz, right? And then we can flip the first two and get minus a minus dx wedge dy wedge dz. In other words, it's just dx wedge dy wedge dz. That's what happened for the first term, the AE term. And guess what? The same thing happens with the other two terms. We always are able to get dx wedge dy wedge dz here, just like that. Of course, this one is easy. It's just dx wedge dy wedge dz. But the other one, we have to move the dy. Well, I guess we have to move the z 2 places over to get past the dx wedge dy. What's the significance of what I wrote there? What is that in purple? It's a scalar. Very good. What is the significance of the scalar? This is the what? Yeah, this is the dot product of ABC with EFG. In other words, the identity here is the identity to extract from what we're doing is simply the following. The flux form of A wedged with the work form of B is just equal to A dot B dx wedge dy wedge dz. Simple as that. So the wedge product also picks up dot products. It has cross products, it has dot products, right? So what is the meaning of the triple product then, with this in mind? Triple wedge. What is the triple wedge of one form? So omega A, wedge omega B, wedge omega C. Well, this is the flux form of A cross B, wedged with the work form of C, right? Which is exactly A cross B, dotted with C, dx wedge dy wedge dz. In other words, the significance of the scalar is that it gives you the volume, which is spanned by these vectors A, B, and C, right? So if I want to calculate the volume, I just take the triple wedge product and I have it. Just like you guys could take the triple product, right? So that's also there. There's another thing we can do just at the algebraic level, which is interesting, which is known as Hodge duality. Hodge duality is very interesting. Here's the way it works. The Hodge dual of the work form of F is, wait for it, the flux form of F. The Hodge dual of the flux form of F is the work form of F. The Hodge dual of the the volume form G dx wedge dy wedge dz is G. The Hodge dual of F is F times dx wedge dy wedge dz. Hodge dual is also nice to introduce if you want to write like slick formulas in terms of differential forms. So I mean, basically the story here with the Hodge dual is that it takes a p form and it maps it to a 3 minus p form. What is it? Yeah, the asterisk is the Hodge. Now, some people, in my current advanced calculus, I've been using a star for it. Some people use star sometimes for Hodge dual because we use asterisk for like many things. But you see that the Hodge duality makes sense, like a one-to-one correspondence between these objects makes sense because like here you've got one of these kinds of things and one of those kinds of things, and you've got 3 independent kinds of one forms, you've got 3 independent kinds of two forms, so you have a natural correspondence between these two objects. Now both of these appear as just plain old vector fields for us in our study of calculus 3, but in fact some vector fields really naturally correspond to one forms, other vector fields really naturally correspond to two forms. So like you guys always have a problem. You got a vector field. What are you going to do with it? Are you going to integrate it over a line or are you integrate it over a surface, right? You got choices. Well, the good news in here is if we're going to integrate differential forms, if I want to integrate a p form, there's only one kind of thing I can integrate it over, a p-dimensional subset of n dimensions. It's like a one form I have to integrate over a curve. A two form I have to integrate over a surface. A three form I have to do an integration over a volume. That's the way that the integration of forms is defined. But I'm getting ahead of the story here a bit. I think that's about all I have to say about Hodge duality for the moment. It has nice properties that are not terribly relevant to us, but the Hodge dual of the Hodge dual is back where you started again, right? The way I've defined it. It's generally plus or minus where you started in other spaces. Okay, now, that's the algebra in a nutshell. What's next? What do we do after algebra? What kind of calculus? Business calculus? I'm not talking about almost calculus. I'm talking about calculus. So, no, the next thing we do is we study differential calculus, okay? So this, in this context, is played by what's known as the exterior derivative. And here's the way it works. If I have a one form that looks like this, I'm just going to write a general formula for you for just a second, if you don't mind. Suppose you have alpha is like a sum over I of alpha sub I dxi. So this I'm just using as like a shorthand. So this dxi would generally be something like dx I1 wedge. Oh, I'm sorry, my eyes are up again. Well, if you don't mind, I'm going to leave my eyes up. That's where they're supposed to be. These are not powers. These are just indices which are written upward. Sorry, that's just, nature of the beast. Okay, so if it bothers you, you can write lower I1 through IP, and it's fine for here. Now, the differential, or the exterior derivative of alpha, is equal to just the following. Sum over I of d alpha I wedge dxi, just like that. So basically, the exterior derivative, and here, this is just the total derivative. So actually, you've already taken exterior derivatives in this course, believe it or not. I mean, I think I talked about this a little bit another day. I'm sorry if I'm repeating myself from that other day, but I was trying to make this lecture self-contained. So we've calculated total differentials earlier, right? And we know how you can use them to estimate error and other things. But I know this is kind of cryptic. Let me unravel that with an example for you. A few of them, actually. So if I have f is equal to x squared plus yz, df is equal to, well, you know the drill, 2x dx plus z dy plus y dz. Now, if I take another derivative, if I take d of df, that's where it gets interesting, right? So I've got d of 2x wedge dx plus dz wedge dy plus dy wedge dz. Let's smell the roses here for a second. So D basically does what? It takes us from P forms to P plus 1 forms. See what happened here? Here we had a 0 form, and this was a 1 form. This in principle is a 2 form. Right? I mean, it is a 2 form, but it's kind of a boring one. What does that work out to? Pull the 2 out, right? dx wedge dx, and oh, oopsie, these cancel, right? 0. Interesting. While we're at it, can you see any significance to this this calculation? How does that? I mean, this is the work form of what vector field? 2x, z, and y, which is the work form of what as it relates to f? Yeah. Well, they're not 0, but they cancel because this is minus dy wedge dz.
Oh.
Yeah.
But the dx wedge dx.
dx wedge dx is itself 0. Yeah.
It's the gradient of that. Right?
I have a vote for the gradient. Do you guys agree? I agree. Yes, that's the gradient of f. So the total derivative naturally encodes the gradient through the work form mapping. Yes, this is generally true. My next example, how about this? Let's start out with alpha equal to, I don't know, y dx minus z dy plus z squared dz. Calculate d alpha. What do you got? Let me make this a little bit more exciting. Let me make this first one like yz. So we have a little bit more to do. All right, so the exterior derivative, what you do is you take the total differential of the coefficient and you wedge it with whatever differential is already there. So do you see what I meant by this definition over here? It's really, all you do is just write it out, and you just take the total differential of the coefficients next to the the wedges of the dx's. It's just that. So this is what? This is z dy plus y dz wedge dx, and this is minus dz wedge dy. And here we've got 2z dz wedge dz. Of course, I didn't really need to write that because that is 0. All right. And what do we have here? Let's see, I'm trying to put them in the proper order, which is yz to start with. Do I have any yz terms here? This one. So I've got dy wedge dz. I switched the order to get a plus. And then what's my next thing? A zx. I got one of those, plus y dz wedge dx. Then what? Dx wedge dy, right? So minus z dx wedge dy. I switched the order of dy and dx there to get the minus. So what is this? This is the flux form of what? Flux form of the vector field 1, y, and minus z. I know you guys aren't going to believe me unless I write this out, so if you take the curl of the vector field yz minus z, z squared, that gives us the determinant of x hat, y hat, z hat, partial x, partial y, partial z, yz minus z, z squared, and that is going to give you 1y minus z. You can check it. To get the 1, x hat, minus partial z of z, 1, that's 0. To get the y, I look at zx, which gives me a y. This gives me a 0. There's the y. To get the z, I do partial xc minus, so that's a z, minus z rather. In other words, we have the following identity. The differential of the work form of a vector field f is the flux form of the curl. And I showed you for an example, but yes, it's generally true. That is not a proof for those of you currently taking Math 200. I think by now you realize that that is not a proof, right? How much partial credit do you get for showing an example when you're asked to prove something in general? 0, as it should be. Yes. Sorry. Sorry. I'm not. I don't. I should only be mean in the classes I need to be mean in. It's unnecessary meanness on my part. I'm sorry. I should behave. But it's good that he does that because we have to free ourselves of now. The only bad thing, of course, is for those of you taking Math 200, is some of you know, right? You know that what you're doing is not a full solution. You're just hoping to get partial credit, right? That's the thing, is you can't tell the difference between the student who is giving you an example of what they're trying to prove versus somebody who thinks that that example actually is a proof of the general proposition, right? So if you are going to give an example, it is ever so very important to include the sentence which says, I understand this is not a full solution, but this is all I could find right now. Because the difference between those things being handed in is just night and day for the professor, right? In the latter case, the professor might think you're lazy. In the earlier case, the professor will think you're stupid. You'd rather have them think you're lazy, right? I think anyway. I don't know. Maybe I'm just giving you an argument for not writing anything. Oh no! It's okay. I think I still know it. All right. So, what would be our next example? How about if we had beta equal to, I don't know, how about x squared dy wedge dz? What was that? Oh, it's okay. I was like, what happened to the camera? Okay, so y plus z dz wedge dx and plus z dx wedge dy. Okay, fine. Oh man. All right, I gotta get with it here. So you calculate d beta, what do you get? You get 2x dx wedge dy wedge dz plus dy plus dz wedge dz wedge dx plus dz wedge dx wedge dy, which is 2x plus the z with z, this goes to 0, right? So we get 2x plus 1 plus 1 dx wedge dy wedge dz. So, in other words, we have the differential of the flux form of the vector field x squared y plus z, z is equal to 2x plus 1 dx wedge dy wedge dz. Can you, what is this? That is the divergence. That's right. So what we have then, in general, says the divergence. And there's a general identity. Again, the differential of the flux form of a vector field f is the divergence of f dx wedge dy wedge dz. There's more. So the other thing you study in differential calculus, of course, besides just how to yes?
I was wondering if you could write just the general form for the first example.
Oh yeah, the first example, the general form, good point, is that df is equal to omega of the gradient of f. Now, in terms of the algebraic properties, I mean, okay, so I've showed you how to differentiate the basic objects. We see how we recover gradient, curl, and divergence, all in one foul sweeping thing. By the way, this fact that d squared is equal to 0, that's a general identity. So here's some identities. The differential of alpha plus beta is d alpha plus d beta. It's linear. That's not too surprising. Perhaps it's a little bit surprising. I don't know if it's too surprising. If you have alpha wedge beta, the differential of the wedge product is d alpha wedge beta plus minus 1 to the p alpha wedge d beta. So here I'm assuming that alpha is a p form. It's also true that d squared, d of d alpha is equal to 0 for any form. It's kind of fun to just stop and appreciate what this d squared equal to 0 means to us in terms of vector calculus. So let's just stop, smell the roses here for a second. D squared equal to 0. So what happens if you look at d of d omega f? What does this say? This says the differential of the flux form of the curl of f is equal to 0, right? Which says what? The divergence of the curl of f is equal to 0. Good to know. We proved this before. On the flip side, you could look at d of df itself, little f. What this is? This says d of the work form of the gradient of f is equal to 0, which says then the flux form of the curl of the gradient of f is equal to 0. Good news, the only way, I'm sorry, there's still a dx wedge dy wedge dz technically here. And then the next step would be this. So then the next step here is the flux form is actually what's known as an isomorphism. It only maps 0 to 0 because it's 1 to 1 and linear. What that means. So there you have divergence of the curl is 0, curl of a gradient 0, all folded into the d squared equal to 0 identity. There's other cool things, like if you examine the Leibniz rule, for just a second here, so like d of omega f wedge omega g, supposedly is going to be d omega f wedge omega g. And then omega is a what form? P equals what? 1. So minus 1 to the 1 is what? Minus. So the product rule is here kind of surprising. It's plus minus, plus minus, plus minus, depending on the degree of the form. Here it's minus, which is kind of cool in the sense that if you can recognize what's going on here. Now this was the flux form of f cross g, right? So we're looking at the divergence, the exterior derivative of the flux form of the cross product is equal to what? This is what? This is the flux form of the curl of f, right? Wedged omega g minus omega f, wedge the flux form of the curl of g. What is this? Well, this is the divergence of f cross g dx wedge dy wedge dz equals to what? This is the curl of f dotted with g times dx wedge dy dz minus f dot the curl of g dx wedge dy wedge dz. And then you can drop the dx wedge dy wedge dz, and out pops this identity we derived earlier through rather different means. So that minus in that identity can be seen as being one of the consequences of this more general so-called graded Leibniz rule. Okay, so that's the differential calculus in a nutshell. Good, I still have time. So that brings us to integral calculus. So how does that work? Here's the basic thing. The integral over a two-point set of a function is just defined to be f of b minus f of a. So that's kind of a silly case. I'm just saying the integral over a set containing 2 points would be that. The integral of a one form, let's say omega corresponding to the vector field f over a curve c, is just equal to the line integral of f dot dr. So you've already been doing integrals of one forms. Every time we do a line integral, we're doing a one-form integral, or vice versa. And the integral of the flux form, and you can think of these as definitions for our current purposes, over a surface S is going to be the integral over the surface of f dot ds. Finally, the integral over a volume, let's say E, of, say, g dx wedge dy wedge dz, basically you just drop the wedges. That's how you integrate forms. Essentially, you just drop the wedges and integrate. And you have to be careful about orientations, but now, the most awesome thing is there is a generalized Stokes theorem. Generalized Stokes theorem states the following. The integral, all right, over some submanifold, some p-dimensional subspace of R3 or whatever. Actually, it's more general than that, but anyway, of the differential of a form is equal to the integral over the boundary of the manifold of alpha. Now, a manifold is just a funny word for like a generalized surface. A manifold could be a curve, it could be a surface, it could be a volume, hypervolume, whatever. That's Generalized Stokes theorem. This one theorem, which the proof of is not too hard. It's really actually interesting. So let's take it on faith for a second here, though, and see what does the Generalized Stokes theorem say about different cases. So let's see here. So to start with, let's pick m equal to, now here, let's say m is a curve. So we have the integral over a curve of d. Now, if it's going to be integrated over a curve, I have to do, it has to be a function, because that gives me a one form. A one form has to be integrated over a curve, all right? So this is going to be equal to the integral. So I'm saying the curve goes from, say, point A to point B. So the boundary of the curve is the 2-point set A, B. Right? So on the other hand, this is nothing more than the integral over the curve of the gradient of f dot dr, right? Because, sorry, this is the integral of the work form of the gradient over the curve, right? Which is then the line integral, but on the other hand, it's equal to f of b minus f of a. So there you go. In the case that the manifold's a curve, you recover the fundamental theorem of calculus for line integrals. If you look at the one-dimensional case there, you just get back the plain old ordinary garden variety. What's the word? Fundamental theorem of calculus. What if we do the same thing for a surface? Take M to be a surface. So we'd integrate. I'm going to do the boundary of S on boundary of M on this side. Boundary of S. So the boundary of a surface is a curve. So I could look at the work form of a vector field. That would be equal to the integral over the surface of the differential of the work form, right? By Generalized Stokes theorem. But this is equal to the integral over the surface of this. So what's this give us? Well, this gives me the integral of f dot dr when you translate back to ordinary calculus. And on the other side, we have the double integral over the surface of the curl. In other words, the ordinary Stokes theorem. Finally, if we take m equal to a volume, if we take integral over the boundary of the volume of, say, the flux form of f, that would be equal to the integral over the volume of the differential of the flux form of f. But we know that this gives us the surface integral over the boundary of E of f dot ds is equal to the integral over the volume of the divergence of f. Dx wedge, dx dy dz, which of course you can recognize as the divergence theorem. So what I'm telling you is the fundamental theorem of calculus, Green's theorem, Stokes' theorem, the divergence theorem, all of the integral theorems of calculus are really the same theorem. They're all the Generalized Stokes theorem, viewed properly through the lens of exterior calculus. So I think you can see why this is the dominant viewpoint if you want to study math in higher dimensions, because this is not bound to cross products in 3 dimensions at all. You can do this calculus in 10 dimensions just the same, and that's why string theorists do that. Anyway, thanks guys. Have a good weekend.